Hey guys, this will be episode 2 of the, amateur makes a OS boot sector whatever series we got going on here. So this is where we last left off. We just jump repeatedly to our same memory address here. We run box. When we boot the thing, it sees the magic number at the end, AA55, at the end of the first 511-12 bytes. We continue box, and bam, it boots from a floppy. It's just repeating there, as you can see from the cursor. So we're good. We didn't tear up our progress from last time. So this episode will be probably split up a little bit, and you'll see clearly where that happens. But we're going to print strings and characters from our boot sector here, still in 16-bit real mode using assembly. And we'll use some BIOS interrupts to do that, and maybe a couple graphical things. We'll change the window size and color, why not? Or some other things. There's a good amount of BIOS interrupts that you can look up for x86 or IBM PC compatible things. But anyway, for this here, we'll start by printing a character, why not? And for that, we're gonna need our BIOS interrupt. I'm just gonna call it a boot sector that prints a character using our interrupt 10, which is for video mode, hex 10 rather. So it'll be 0x10, I guess. And then for these, you put different values in the registers you get. I guess I could talk about registers too. I'm just gonna put this to begin with, 0x0e. So in assembly, your CPU, as far as memory locations, it has some registers in it, and these registers are a lot faster than your main memory and than your RAM even though your RAM's pretty fast. These registers are built into the CPU itself, and you can move values to and from there. There's also cache, and you have levels of cache, but I'm not getting into that because we're not using them, I think. But we have registers such as AX, BX, CX, I can't type, and DX. So these are 4 general purpose registers that you can use for generally anything. The AX may be the accumulator, and these other things have different general set values that they're used for, but in general, they're general registers that you can use. And this is in 16-bit mode. And each mode that your CPU will be in, 16-bit real mode that starts up in 32-bit protected mode, or 64-bit I think is long mode. That is the size of the registers and operations that can occur on them. So in 16-bit mode, you can do 16-bit operations on the registers and using them. Or one word, which is two bytes, 2 sets of 8 bits, 16-bit, right? But basically these registers we'll go over more later, like segment registers and stack and base pointer and stuff. But just for the purposes of these next couple videos, AX, BX, CX, and DX are general purpose registers that we're going to use. And these are 16 bits in length, 16-bit long, the size of them. So they're 1 word in length, 2 bytes, 8 bits and 8 bits. And you'll see that because you can also access each 8-bit portion of these registers. So you'll have like a high and a low bit. I guess it'd make more sense if I maybe split it out. So 1, 2, 3, 4, 5, 6, 7, 8. And it gives it different colors, which I guess would be helpful here. But we'll say this is our AX register up here. I'm going to get rid of this other, well, I'll just put it down here. So we'll say this is our AX register. You have 2 sets of 8 bits, right? You have the high bits and the low bits, as it were, the high 8 bits and the high low bits, and these are called AH and AL respectively. And the general purpose registers are made up like this. The other ones I don't know, but that's what these are called if you go down to the lowest 8-bit forms. In 32-bit protected mode, I think it's EAX. Your registers are instead called EAX, EBX, ECX, and EDX, and they are then 32 bits in length. And then to access the upper 16 bits of these, they are AX, BX, CX, and DX. The lower 16 bits, I don't remember if there's a difference or not. There probably is, and I'm telling you dumb stuff, but oh well. But it's made up of that. 64-bit long mode, I believe it's RAX, BX, CX, DX, so on and so forth. But we're going to be dealing with AHAL and possibly BHBL, DHDL, maybe even CX. I don't know, but that's just what we're going to be using. Those are memory locations, they're registers. memory locations built into your CPU, so they go really, really fast, and they're generally really nice guys, so that's good. But the BIOS interrupts, which is why I went into that spiel, the BIOS interrupts use these registers to set up values that mean certain things. So, for instance, our int10 AH0E in hex is the BIOS teletype output. And that involves putting, well, you call int10, to call an interrupt, you call int10, but to call the BIOS teletype output, in particular, that interrupt, which puts a character at the cursor and then advances the cursor by 1. So it'll put a character and then move it to the next place for the next character, say. For that, you set up, you have your AH register. We do a move instruction, actually. You do a move and you put into your AH register, your A high, the upper 8 bits of your AX general purpose register. You move hex 0E. So 0x0e or 0EH may work as well, however you want to write it. I think I'll just write it here as well. int10 0x0e. So we move that into the AH register and then into the AL, the lower 8 bits of our general purpose AX register. We're going to move the character we want to type. So it can be really any valid ASCII character, although if it's not a visible one, like a line feed or something, you're not going to see it, really, unless you know where the cursor was. We're just going to put a T for test, I guess. Put character we want to print, and then we called the BIOS interrupt with the int instruction here, hex 10. Which is basically BIOS, I think it's, I don't know, video interrupts or however it's called. I don't remember the right name at the moment, but this will basically print a T to the screen. So if we do this, we should see a T pop up on the screen, I believe. Or else I lied to you, which that might happen too. I'll try not to make that happen too often though. So let's boot up here, and there we go, we get a T, so. That's really all you need to know for BIOS interrupts, right? But they're all pretty much that easy. You're just setting up values. Usually it's more than 2 for the more advanced ones. Like I think there's one to print a whole string. Maybe I'll show that. And that you need to set up, I think, the length of the string and BH or BL, stuff like that. But just for printing a character, all you need is AH and AL. You only need the AX register, really. So that's pretty good. And I'm assuming since AX, the register is made up of AH and AL, and that's contiguous, that's, connected. I'm assuming if you just move the hex value 0E and then T in hex, and you just move that all into AX, then this would work. So let's try that. Let's try, instead of these, move the cursor out of the way. Let's move into AX the value 0E54, because uppercase T in ASCII is 54 in hexadecimal, so maybe we'll see if this also prints a T. So prints a T, question mark. If so, then we're kind of smart, maybe. I don't know, probably not. We can Google, and all great engineers Google. And see, there you go. So if you want to code in straight hexadecimal, well, you're still one step removed, but you can do that too. This does print a T, 0E and AH, T, and AL. So that's cool. So you can do that if you want to as well. It's a one-liner, and people love their one-liners. It gives them job security. Not that I know anything about that. So we're going to exit here. So that's how you print one character. Now if you want to print multiple characters, all you would do is really just repeat what you did. So, you move the T into AL. AH won't change in this case, in this instance. AH shouldn't change. And we can make sure of that in a little bit, but we can just keep moving our other characters into AL. So I'll print like test, right? I'll just keep moving letters into the AL, the lower 8 bits of our AX register, and you have to call the interrupt every single time you want to print, because it's more you're setting it up and then you're calling, kind of like a function, sort of. So we have to call the interrupt after every character we want to print, really. At least for single characters like this. But we'll do TEST. And there you go, and that should print test. Start off very slowly so my brain works this morning. There we go, so that's test right there. So just moving our letter into AL. AH is hex 0E, and then calling the interrupt 10, hex 10. And that's how you print characters. It's pretty simple. Hopefully it seems simple enough. So that's how you print single characters. So I guess I can go over, I don't know, loops, well, strings. I can go over full strings, right? Let's do that. So how do you print like a full string from assembly? Let's do that. We're gonna use a label here to hold our data. So you see here we have a label called here and jump here, and I'm just gonna change this right quick to jump $, because that'll do the same thing. Keep jumping to here, never-ending loop. This will halt the thing. It just jumps to the current memory offset, so it'll keep going to itself. It does the same thing, jump $. But say you want like a variable or something to hold a string, you'd use a label like we had here, colon, you'd use a label. So I'm gonna call it like a, I don't know, TestString. So you give it a thing, you give it your name, you give it a colon, and you'd use db, or you can use db, define byte, at least for this one. We're gonna find it as test, or maybe just, I'll start off with the character again, T, and we'll end it with the 0. I'll put 0/null to null terminate. So, and the reason we end strings and stuff with null, or the 0 byte here, is so that we can have an easy check to see where the end of the string is, because that's not going to be an ASCII character, 0. It won't print anything, be garbage, but we can check for it and use that to see when we should stop printing our string. So, but the way we do this is our labels here are basically, it's not really, you use the name, but it's more of just like a formal name for an area in memory. Not the values within that, which would be a T, but the memory address, like, you know, hex, I don't know, 805221, it doesn't matter. That would be like this memory address, and then the value at that memory address would be this T here, and the 0, so it'd be like 2 bytes, but that's basically all labels are. They're just memory addresses that you can refer to later to make things easier on yourself. So if we have our test string here, we're still going to use hex 0E for AH, the A high, but the A low, we're going to move in test string, so the value at memory register text string. I'm going to put that here, or the memory itself, I guess I've heard some sources call it. I'll put memory at address test string. So we're moving that into AL, and then we're going to call the BIOS interrupt. I think this will work. If it doesn't, then I'll just cut it out. But the pad does 2 passes this time. I believe Phasm first goes through it and gets the labels and everything, and then on its second pass, I think it resolves the labels to memory addresses, I think. Now this might not work. It might print garbage or nothing, or it'll keep zooming on along. So this is cool, and it prints like 3 lines in a row, like the settings hamburger, some kanji or something. So why did it do that and not print what we wanted? I'm glad it does this actually, which is nice. So in NetWide assembler, I think it does actually resolve things and print where you want it to, but flat assembler is closer to the regular x86 spec, at least for 16-bit real mode. So you can't just print stuff from anywhere, even if you set it up correctly, quote unquote. It's still going to print from, I think, arbitrary locations, even after it's set up. And to do this, I think I briefly went over it last time, but your BIOS code is normally loaded in hex 7C00. So what you can do is give an instruction to start off hex and tell it org, which I think means origin. I think in NetWide assembler you surround this with brackets, if I remember right. But in flat assembler you don't need to. But org, which tells you like where the BIOS code starts. I think it's origin. If I'm wrong, then, you know, forgive me. But I'm just gonna put it here so I remember. Origin of not a BIOS, of our boot code. And this helps. This helps make sure any addressing that we set up does not change. So we put that here, and it basically says, hey, you're supposed to start at this location, and then the assembler will set up our labels and our things, our memory addresses, basing off this location. So test string would be at some offset from original location 7C00. And that means when we go to print or move the value at that memory address into AL, it would actually take our T in our 0. And it would not, for the purposes of this, we don't need the 0, but we're having it here anyway for later. But it would take our t into there instead of just some, you know, the 3 lines that we got before. So this should work because we're formally setting up our memory here pretty much. And it should print. Oh, it does not. Oh, well, that's good. It prints a t. Hey, it still goes through all this stuff, but it does print a t, and that's always nice. So why is it still looking through memory when we don't really care? Well, it looks through until it finds a t and it prints it, and that's nice. To make sure that doesn't happen, we're going to use another register, which is, I guess, traditionally used for this kind of stuff, for indexing. What we're doing here is we're sort of indexing our test string memory address at offset 0. So we're not really going from it, but we're still using it as an index to get the value into our AL right here, right? So what we're going to do instead of that is basically do the same thing, but we're going to move the address of test string into our BX register. Now I think in NetWide assembler you can use whatever general purpose register and it's okay, but for this we're going to use BX because that's, I think, what it's traditionally used for indexing, and flat assembler doesn't like if you don't index the BX register in 16-bit mode. And 32-bit and long mode, I think you can use whatever, but for this we're going to use BX, right? That probably made no sense, but we're moving or copying, but I'll put moving memory address at test string into our BX register. And then instead of test string, we can get the memory at the BX register instead. And it should do the same thing. Maybe it'll work a little better, maybe not. I don't really know. But it's basically the same thing. We're moving this address into this address. See, we have different addressing modes, which I didn't mention so far, which is great. I forget if this is immediate mode or not. I think just using a number is immediate mode in flat assembler, but this is memory addressing, maybe indirect, and this is direct. I forget what exactly each of those mean. Apologies. All I know is that this stuff kind of works. But we're taking the value at the memory address in test string that we moved into BX, and we're putting it into AL. And what this does is it moves, when you do it like this, see, BX is a full 16 bits long. Even though AL is only 8 bits, normally you can't do that. But when you take the index of it, and when you're getting the actual memory at that address, at that index, it's only taking 8 bits. It's taking 1 byte at a time in this case. So we're moving a byte into AL, and this byte happens to be in the same location that we can move. Well, the byte in BX, it's confusing. The byte in BX, the first byte is T. It'll be T, and then 0 will be the second byte, and the second 8 bits, right? So the first 8 bits is a T at this memory address test string. We're moving, and since we're copying the address into BX, BX now equals T and 0. And the first byte of that is the T, and that's what we're moving into AL. If we did something like BX plus 1, that would move this null, because you're offsetting it by 1 byte, I believe in this case. You would move this 0, this null, into AL instead. But we're not offsetting it all at the moment. We're taking the beginning, and that is the T. So that's basically, we're moving a byte at a time. This T goes into here. Hopefully that made sense, because I said it kind of bad. Print a T. No, you don't want to. Wow, it really doesn't like me today. That's pretty awesome. It does print the T though, but then it keeps moving to non-existent segment register 7, which is, we don't really want, but that's okay. So if we want to print more than one character at a time, we can put it all in our test string here. It just means we'll either go through each character by character, so we can do it like this if you want to be archaic. We can use offsets. This is one way to do it. Add 1 byte. It doesn't really add, but we're getting the value at a 1 byte offset. BX address. Well, the memory address is in BX now, so I'll say this. Move into AL, and this should be the E. But we can also do, we'll call the interrupt here to actually print the character. Or you can do an add command, an add instruction, and we'll add 1 to BX itself. And this, it kind of adds 1 byte. I'll put like moves forward 1 byte at address BX, at the address itself. So this one is indexing the value that is 1 byte behind or ahead or however of the start of the address in BX, so which is TestString, but basically the first thing you get right here is the T. If you move 1 byte, it's going to be the E. And this one, you're taking the address itself, which is still, at this point, the address still starts here, but you're taking this one. Here, you're adding 1 to the address itself, so we're moving forward to this. So this would also print an E if I moved it into AL. So what I'm going to do is just add a 2, and that should move it to the S, go 2 bytes. So now the address is pointing to this part right here. And we're going to move that. The value that BX is pointing to at the moment should be an S. So hopefully that works, but I'm putting S there. And then we'll just do this again, why not? Because it's fun. No, not really. No, it is fun. I like learning about this stuff. It's probably really boring, but oh well. And this will be the final T. And this should print out test, I believe. We're still not messing with the null byte we put on there, but that's okay. And it'll still probably jump around in memory, I guess. Right? It does. But when it reaches our code, it should execute it. There we go. See, it prints test. So we're good. We still print test. That's another way to do it. Now this can get very tedious and long for big long strings, so we don't really like doing it this way, but you can, and it works. So I guess a better way would be to use labels, or maybe a more structured way could be to use labels in this, in a loop, basic loop structure. And that uses jump instructions like we have here. So we're still going to set up 0E in our AH here. We're still going to move TestString into BX. But now we're going to sort of, I guess we can call or we can jump. I'll start by jumping to it. We're going to make a section of code called print string. I'm going to get this stuff out of the way. I'm going to put it here. And what I like to do for just like kind of variable labels, which I'll just put a thing here. I'll call it data, I guess, or maybe variables. I don't know if variables is the right word, but we're kind of using it as a variable, so I'm going to call it that. I don't know. But the section of codes, I like to indent and go below it, but when I'm using stuff kind of like variables, I like to put it on the same line. That just helps me differentiate, but styling conventions can be argument territory, and I don't like to get confrontational. But we'll just have a section here, print string, and we're going to move whatever's at BX. We're going to move the value into AL. I guess I should comment every line, right? Because it's assembly. Although jump print string, hopefully that's straightforward. You just jump to this area. It's like a goto if you know what those are. It jumps to print string here. Move character value at address in BX into AL. So we're going to do that, and then we're going to compare. I'm going to use a compare instruction here. We're comparing AL to null or AL to 0. So this will, I think it sets a 0 flag or an equal flag or something, some flag in the CPU, because it has special flag registers that it uses as well for the result of some operations. I think this sets one of those off, but anyway, you're comparing AL to 0. If that's true, then a flag will be set off, and you can use that. So we'll do like jump equal is what this is, JE, and what this means is jump if equal. So if AL is equal to 0, if that is true, then this will jump to wherever we tell it to. So if that's true, I'm just gonna put in program, I guess, or halt or something. I'll just do in program. Jump if equal to halt label. And I'll put a label here. We're putting a lot of labels, but it helps structure the program ultimately. So we're just doing this. This will jump here and do the regular. I'm gonna call this bootsector magic because it's the magic number. But when AL reaches 0, we're gonna jump down here and basically end the program. We'll just jump repeatedly. If AL is not 0, then that will not, this instruction here will not occur. It'll basically read it and skip over it because it's not true. And if it's not true, then we're gonna print the character we got, print character in AL, and then we're gonna add 1 to BX. So move 1 byte forward, This will get next character, or get the next byte from our BX address. And then at the end, we're gonna jump back up to print string. And this basically makes a loop in assembly, a basic loop. So we're gonna get the value at the memory address that's in BX, which is TestString. So it'll be a T. We're gonna compare it to 0. That'll be false for the first one, but if it does reach the end, we're gonna end and jump repeatedly. If we're not at the end, we're gonna print out the character that we moved into AL, and then we're gonna move to the next character from the address. So it should print out test and then jump repeatedly. If that makes sense. Hopefully it does. I'm gonna change our heading here to prints characters. Haha. And labels. And this is good because it sets up an easier way to make external functions and stuff. This would be a good segue into that, which I'll probably use later. So there we go. See, it prints test. Does the same thing, just using a loop this time. And if you were fast with your eyes, because, you know, it's slower being in a VM, and then in the VM we're emulating a full x86 PC and CPU, you could see it print out. Does it fast, but you can still see it. But that prints test as well, so that's pretty good. But that's really pretty much at this moment how you print basic strings. You'll move your addresses into wherever you want them, set them up. You'll move the values at those addresses into AL if they're characters and you want to print strings and stuff. If you're wanting to use the BIOS interrupt for teletype output, which is what I'm using, which is int 10 or 10H, you might see it online, and then AH0E. But that's how you do that. Hey, I'm back. I just wanted to do a couple more small things for, I guess, to top off this episode here, to further bring the point home that this is basically technically a function. It's kind of self-contained here within print string. It's both a memory address and pretty close to being a function, just not calling it as such. We have test string here. You can print any number of strings. We can have like string 2 db, also a test. We'll make it, you know, an arbitrary length here, however much it is. So we print the first string here, we jump to it, move bx test string, we jump to it and we call it. So now what we're gonna do, well, we jump to it, not calling it, but now we're gonna call it. I'm gonna call test string instead right here, and what calling will do is automatically return. I think it pushes the address, like where you're at here, onto the stack, and then it'll go through what you called, and then when you reach special instruction ret for return, it'll go back to where you called it, and the address will be popped back from the stack. I believe is how that works, but basically it saves the address for you, and it's a little nicer like that. You don't have to keep jumping back and forth. But this does mean that we can also do multiple strings very easily. So we just move the next string into BX, and then the print string already handles printing it and moving it into AL and all that, calling the interrupt. So we do that, we're gonna call print string again, and then after we return from that one, we're going to jump to the end. We'll just jump to end program here. So printing multiple strings using call and return. We don't need to do this anymore, I suppose. Let's do another label. Let's just put a bunch of labels. We'll call it end string. So instead of ending program here, we'll end printing the string. I guess maybe end print would be better. Let's do end print, because that kind of better describes. We're not at the end of the, well, we are at the end of the string, but we'll just do that. That'll be the return. And we'll call this again, but after that's done, we should end. So hopefully this is good, and we'll print both strings. I'm gonna print the second string after the first, and when I say after, I mean on the next line. So how do you do that? Well, in Unix, you generally have line endings of CRLF, carriage return, and line feed. I think Windows is just one of those, but maybe just LF, but it also works. Or maybe Windows is both, and then Unix is just the carriage return or just the line feed. I don't remember exactly, but to do that, we're using the ASCII codes, which is 0xa and 0xd. I forget which is which, but one of these is carriage return and one of these is line feed. Carriage return basically takes your cursor to the beginning of the line that you're on. So it would be, the cursor would move all the way to the front like that, and then line feed moves down a line. So it would just start printing after this on this line, and then when we print the next string, it should be on the line below it. So hopefully, that's why we're putting that there. Or it won't because I messed something up, which is usually the case. But no, we're good. See, we have test and also a test. So there you go. 0 hex, 0xa, 0xd, or hex A and hex D, carriage return and line feed, and ASCII codes. I believe they have to be uppercase, although maybe that doesn't matter. They might not have to be uppercase, so disregard that. But I do them uppercase, and it makes sense, and it works, so. I guess we're good on there. So I'm going to, I guess, do a couple other, maybe 2 other BIOS interrupts, just to show that it's not just printing strings, printing strings. Interrupt 10, which is what we're using here. Interrupt hex 10, or interrupt 10 is, hex 10 is decimal 16, I believe. But that's just for video stuff in general. So maybe before we print the strings, we can do, we can set the video mode, which I believe I'm gonna do. AH is 0, AL is, let's do 3. So AH is 0. Let's do int 10 AH 0 is set video mode, and we're going to use, you can look all these up as well under interrupt 10, int 10 in the BIOS, and you can see all the different stuff you can do with it. But we're gonna move 0 into AH, and AL, let's do 3, hex 3, and this should be, I think, 80 by 25 and just regular text mode maybe, and not graphics mode. So we do that, and then we'll call the interrupt, and that should resize our window before we call the other stuff. We'll just call this set video mode. Prints characters using BIOS. I'm just gonna do interrupts. And then the ones below this point will be teletype output. So this should resize our window and clear it, although I don't think all of these clear. I think setting the video mode usually clears the screen, and then if you do one of those where it scrolls enough to scroll past the screen in your video mode, then that would clear the screen. So for this one would be, I think it's 80 rows by 25 columns. So if you were to scroll past 80 rows, that should effectively clear the screen as well. But so this should resize the window and clear it before printing. So the only things we should see are the 2 strings here, which I'm touching my screen again. I like how I do that. And it did. So it cleared it first, and then it wrote out the strings. So that's a way to clear your screen if you want to set the video mode, which is kind of slow. I wouldn't write games doing video mode interrupts, because there are interrupts for writing pixels, like graphics pixels, but you don't want to do that through this and looping. That'd be very slow. Even in very fast emulators and modern PCs, that'd be probably too slow. So you don't want to do that. Definitely may not reach like 60 FPS on that. But that's just setting the video mode. And then another maybe fun thing we can do, let's change the color. Let's do that, which I have to look it up again. That's why you always use references, kids. It's really nice. 0B is set color palette. So I'll put /palette, depending on the video mode you're in. If you're in text mode, I think it sets the palette, and then graphics mode, it sets the color, or the opposite. It's probably the opposite, but we use 0B for this, hexadecimal 0B. And then we move that into AH, A high, and then into BH, into B high, we're gonna move our palette color ID, which sets either the color or the palette. Background and border, we'll move 0 into it to set the color and not change the palette. And then into BL, we're gonna move our color value or palette value, depending on if BH is 0 or 1. I think 0 is the current color, so it wouldn't change. It'd stay black in this case. We'll change it to 1, which might be green or might be blue. I don't remember. We'll find out. And then we'll call the interrupt again. So use AH, BH, and BL for changing the color for this BIOS interrupt. And I am still recording. Sometimes I hit a hotkey and it changes that, so just making sure. So this should make it blue, and it's blue. So that's good. This is also a test. Now it looks like the screen didn't change from our last one, but that's because we're already in, I think, default 80 by 25 character mode. So if I were to change this to 1, you'll see that this one's actually working for the video mode. If I change it to 1, I think it's 40 by 25, so it'll be a little skinny mini. And it is, see, so that does effectively change the video mode here. Just wanted to make sure that that worked, and it does. And we also get the nice bar up here that I've left. That's good. Definitely not an emulator. No, it's being emulated. But yeah, test. This is also a test. We're good. So that is how you print multiple strings. You just, you define your strings, or however you want to send them to your print string thing. That's almost technically a function. You're calling it like a function, it's returning, so I mean it kind of is. Maybe it's more, you can think of this sort of thing here, calling and then returning after and doing all the calculations, whatever. It's kind of like a subroutine or sub-procedure, which we use a lot at work, so I'm used to stuff like that. But yeah, print multiple strings however you want, and, mess with some BIOS interrupts, cool doohickeys like that, yeah. So that's pretty fun. I think that's all I'm going to do for this. Probably drag on long enough. Has drug on long enough. That would be English, which is good, which I speak effectively all the time. But yeah, that's all we're going to do for this. Just multiple strings, mess with BIOS interrupts. The next one that I do for this video, whatever, I'll probably print hexadecimal, which isn't that hard. It's just converting hex to ASCII and doing the same thing we're doing here. So I'll print hexadecimal characters, which is useful for debugging if you figure out how you want to do debugging, or at least get an idea of it, because it can help a lot. Printing hex either to see values or addresses, which you can use hex for. Convert back and forth, and then we'll also use, I think, external files. So we'll move our print string into an external file and call it from this main bootsector assembly file. And then that'll be, the world's your oyster at that point. You can just, call things all day and build out your stuff as you see fit, because you're not confined to one, giant 10,000 line file or however you want to code. But yeah, we'll do that. We'll print hex and have external function calls and stuff. So that'll be cool. And then we'll take it from there, I guess. But yeah, thank you all for watching. I will see you on the next one.